Alright, now we are moving to the complete version of the Bayesian variable selection or stochastic variable selection model. Okay, there are two key differences. Now here we are sampling this P parameter and B0 and B1. Right? Okay, so then as always we begin with model description or the data generating process. Okay. Okay, in the first stage, P is generated from this beta distribution. Previously, it was fixed, right? It was fixed at 1/2, right? But now this is the parameter to be simulated or estimated, okay? And what does it mean by P, okay? You see that previous P was the prior probability of the gamma K, okay? And please notice that here, there is no subscript in P. Each gamma has its own subscript K, right? But there is no subscript P. And then P is the probability of the gamma K being 1, right? So it means what? P determines what? P determines the overall probabilities of the importance of each variable, or this is identify the number of important regressors among the potentially among the potential regressors. Okay, so then P is just a portion. P is a portion of important regressors among the all regressors considered in this regression. Okay. So now previously it was fixed to 1/2. Now we have no idea. So we are going to estimate P because P can be quite different from 1/2. Okay, it could be close to 1 or 0, right? So we would like to update P using the data, right? Okay. So again, so we are sampling P now. Okay, and then given P. Okay, P is generated from this beta distribution. So prior distribution of P is beta, and given P, the gamma K's are determined. Okay, gamma K's are 1 with the probability of P and 0 with the probability of 1 minus P. Okay, right here. No, okay. Right. And now we are sampling B0 and B1. Right? B0 is what? B0 is the prior variance of the beta when what? When gamma K equals 0, or the case, or you say the Sk is not important, and B1 is prior variance of beta. Okay, when what? When gamma K equals 1, or Sk is important. Okay. So the B0 and B1 are both generated from the gamma distribution, but their hyperparameters are different. This one is alpha 0 and delta 0, 0. Here alpha 0, 1 and delta 0, 1. Okay, and then this is really important here. Prior mean of B0 is very close to 0. Okay, whereas the prior mean of B1 is quite bigger than 0, right? Previously, B0 was fixed. Fixed at what? Fixed at a very small number. And B1 is fixed at a large number. Okay? So instead of fixing their values at some particular values, we are sampling B0 and B1. So again, here we are updating B0 and B1 using the information in the data. Okay? So given B0 and B1, then now finally beta is generated from this normal distribution. Of course, it depends on the value of gamma K. Okay? If gamma K equals 1, then prior variance of B0. It means what? Beta K can be any value. This can be far bigger or smaller than 0. But if gamma K equals 0, then gamma equals 0, then the prior variance is B0, so that beta K is generated from this normal distribution with a very small variance. So beta k, realized beta k should be very close to 0. Okay, it means what? Sk will be treated as unimportant regressor. Okay, here, and as always, sigma square is generated from this inverse gamma distribution. And now finally, given beta and sigma square, y is generated from this normal distribution. Here, these are the parameters we are supposed to estimate, right? Beta, sigma square, b0, b1, p, and gamma, right? But when y is generated, when y is generated, we don't need the other parameters. Okay, we need only beta and sigma square. Okay, and these parameters, I mean the b0, b1, p, and gamma, are necessary in generating what? Beta and sigma square. Actually just beta, right? Okay, so once beta and sigma square are given, then the other parameters are not required in generating y. Okay, so this is the model. This is value abstraction model. Okay, again, in the first stage, the overall probability, or just the portion of the important regressors among the variables considered in the regression, is determined by p. So this is randomly generated from this beta distribution. Okay, and this is our belief. This is our prior belief. And then given p, then the probability of each regressor being important. Okay, so this given p, then gamma k is generated with this p probability, and is equal to 0 with this 1 minus p probability. And b0 and b1 are both from the inverse gamma distribution, right? And then beta is generated, and sigma square is generated, and then finally y is generated. This is the data generation process we believe, and we believe that y must have been generated from this process. Okay. Okay. So this is just our prior. This is our prior belief, and then we are going to update our prior about the parameters will be updated by the information data. Okay, so then our goal is to generate this posterior distribution. Okay, to generate this posterior distribution, we compute posterior density. Okay, right? But this posterior density is not standard, right? But they are full conditioners. Their full conditioners of the parameters are standard. That means we can apply the gap sampling method to generate the parameters. So we are sampling the parameters in 6 blocks. Here, beta, sigma square, b0, b1, p, and gamma. Okay, so 1, 2, 3, 4, 5, 6. So we are sampling the parameters in 6 blocks. Okay. Of course, we have learned how to generate beta, sigma square, and gamma, right? Given the other parameters, right? So now we need to discuss only the sampling procedure for b0, b1, and p, and nothing else, right? The others have been already covered. Okay. Okay. So there's nothing to discuss the beta sampling. Okay, sigma sampling is same as before. Okay, here gamma is same as before. Okay, but the only difference is now here you can see now the gamma k is now conditioned on b0, b1, and p. Right? Previously b0, b1, and p were not random variable. Now here these variables are random variable, and then these variables, or these parameters are are changing across the iterations, right? Okay. Okay. Here now we are sampling b0 and b1. Okay, this is really important. Again, so this is our prior. Okay, when gamma equals when gamma is 0. Okay, so let me explain this notation. So we have beta. Okay, how many? We have capital K. We have capital K beta because we have capital K regressors. So we have capital K beta parameters, right? And among them, we are going to just extract. We are going to just take the beta coefficient with gamma equals 1. Okay. Again, so gamma is given, right? Gamma k's are given. So some gamma k's are 1 and some gamma k's are 0. Right? So then given gammas, we can take out the beta coefficient. Okay, beta coefficient with gamma k equals 1. Right? So suppose we have 12 regressors, and then in the iteration there are 5 gamma k's are 1 and 15 gamma k's are 15. Then gamma k beta gamma equals 1 is what? This is 5 by 1. This is 5 by 1 vector. And here this is what? This is 15 by 1 vector. Okay. Okay. So now this is a vector of the beta coefficient. Okay. With gamma k's are 1, right? And then once gamma k is 1, then this is prior distribution. Okay. So this is model. This is a model for beta, or beta gamma equals 1. Okay. And this is the model for beta, and this is prior distribution for B1, right? And just look at this. This is quite similar to what? So if this is what? This is y. If this is y, and this is sigma square, and there's no mean parameters, right? And sigma square is inverse gamma. And actually this is what? This is just standard linear regression. This linear regression. So beta is now dependent variable. Beta is dependent variable, and there is no regressors. Okay, there is no independent variable, and there is only sigma square, nothing else. And sigma square follows inverse gamma distribution. So that in this linear regression, how many parameters do we have? There is only one parameter. What is that? B1, right? So we need to estimate B1 only. And do we know how to sample B1 from this linear regression? Yes. So this is model for beta, and this prior for B1. And prior for B1 is inverse gamma. And then if we combine these two equations, then still we have what? Still we have the posterior or the full conditional distribution of B1 is still inverse gamma distribution, right? And according to the formula for sampling B1, what? This is what? This is alpha 01, this and before, and plus sample size. How many samples? We have K1 samples. K1 is the number of gamma k's equals 1, right? So in the example, this is 5. This is 5, and this is 15. This is 15. Okay. And this term is what? This term is delta 01 is from here, and this term should be what? This is what? Sum of the squared residuals, right? Sum of the squared residuals, right? And how to compute residuals? Dependent variable minus conditional mean, and conditional mean 0, right? So then what? This is just this beta gamma equals 1 itself is residual, right? So then beta prime times beta is now sum of the squared residuals, right? So B1 is sampled. B1 should be sampled from this inverse gamma distribution. So this is the full conditional distribution of B1. What about B0? The only difference is that now we use beta gamma equals 0, right? The vector of beta this is a vector of the beta case, okay, with gamma case are gamma case equal to 0, okay. So then gamma k0 is the number of the number of unimportant regressors in the particular iteration, okay, particular keep sampling iteration, and this is the sum of the residuals, sum of the squared residuals, okay, right. And then finally we need to discuss the sampling p. Previously it was fixed at 1/2. Now we are sampling p. This is very simple. And then so please try to derive this full conditional distribution, okay, by yourself. This is not difficult error, okay. So this is just the exact same as the coin toys, okay. You mean the okay. Can you remember the posterior distribution of the prob of the head? Okay, using the outcomes from the coin tosses. This is same as before. Previously, it was the in the example of coin tosses, it was the outcomes are also 1 or 0, right? And this same as before. Okay, the prior of p was beta distribution, and its full conditional is also the beta distribution. So k1 is what? K1 is the number of ones, and this k0 is number of zeros. Okay, so then p is simply generated from this beta distribution. Okay, so if k is large, if k is large and k0 is small, then it means what? It means what? The number of the important regressors are more or larger than the number of the unimportant regressors, right? Or the important regressors are more than unimportant regressors. So then p should be large, because p determines what? P determines the portion of the important regressors among the total regressors considered in the linear regression. Okay. So again, so p is just simply generated from this beta distribution. Okay. And then that's it. Okay. And this algorithm 2.1 summarizes the stochastic value abstraction algorithm. Okay, we generate beta, sigma square, b0 and b1, and p, and of course we are generating gamma k, and that's it. Okay, all right. Okay, then now let's make a quote. Okay.